Carbon has one s orbital and three p orbitals. They have different shapes and energies, and yet, carbon can form four equivalent bonds in methane. So here's the mystery. How can four different atomic orbitals produce four equivalent bonds? And why does carbon arrange its bonds at approximately 109.5 degrees in methane? But here's something even more fascinating. When carbon forms a double bond, the geometry changes. And when it forms a triple bond, it changes again. How can the same carbon atom change the arrangement of its orbitals depending on the bonds it needs to form? The answer lies in a remarkable concept called hybridization. Welcome back to Decoding Education. In last episode, we learned that half-filled orbitals can participate in covalent bonding, and that the extent of orbital overlap influences bond length and bond energy. But there's one major question we never answered. How do carbon's very different s and p orbitals come together to produce the equivalent bonding directions we see in real molecules? How does a spherical orbital and three dumbbell-shaped orbitals become a set of orbitals perfectly arranged for bonding? Today, we're going to solve that mystery. Let's start with carbon. Its ground state electronic configuration is 1s2, 2s2, 2p2. And as we discussed earlier, electron promotion gives carbon four singly occupied orbitals, 2s, 1, 2p, 3. So now carbon has four electrons available for bonding. Sounds perfect. But look more carefully. Those four orbitals aren't the same. We have one 2s orbital and three 2p orbitals. The s orbital is spherical, the p orbitals are dumbbell-shaped, and they point in three different directions. So if carbon simply used these four orbitals exactly as they are, we would expect the four bonds to be different. But methane tells us something completely different. In CH4, all four CH bonds are equivalent. They have the same bond length, the same bond strength, and they point toward the corners of a tetrahedron. So something must be happening to carbon's orbitals before bonding. And this is where the idea of hybridization comes in. Hybridization is the concept in valence bond theory where atomic orbitals of similar energies on the same atom combine to form a new set of equivalent hybrid orbitals. Think of it like mixing ingredients. Imagine you have different ingredients, and instead of using each one separately, you combine them to create a completely new mixture with new properties. And this is where the idea of hybridization comes in. S orbital combines with one or more p orbitals and produces a new set of hybrid orbitals. These hybrid orbitals have shapes and orientations that are better suited for forming bonds. And depending on how many orbitals participate, we get different types of hybridization. The three most important ones for organic chemistry are SP3, SP2, and SP. Let's start with the most familiar one, SP3 hybridization. Take carbon and methane. Carbon needs four equivalent orbitals to form four equivalent CH bonds. So one s orbital combines with three p orbitals. 1 plus 3 gives four hybrid orbitals. These are called SP3 hybrid orbitals. Notice the name SP3. The S tells us that one s orbital participated and P3 tells us that three p orbitals participated. And the result, four equivalent SP3 hybrid orbitals. These orbitals point away from the carbon atom in four different directions, toward the corners of a tetrahedron. The angle between any two of these directions is approximately 109.5 degrees. This arrangement allows the bonding orbitals to stay as far apart as possible, which helps minimize electron pair repulsion. And that's why methane has its characteristic tetrahedral geometry. So now, the mystery of four equivalent orbit in methane has solved. But carbon doesn't always need all four orbitals for single bonds. Sometimes it only hybridizes three, and that changes everything about its shape. That's where things get even more interesting. Consider ethene. Here, one s orbital combines with two p orbitals. That produces three equivalent sp2 hybrid orbitals, and one p orbital is left unhybridized. Each carbon forms three sigma bonds. The three sp2 orbitals arrange themselves approximately 120 degrees apart in a plane, which results in a triangular shape, and that remaining unhybridized p orbital is available for the additional bonding interaction involved in a double bond between carbon atoms. We'll explore exactly how that remaining p orbital participates in pi bonding in the next episode. For now, the important point is sp2. Hybridization gives carbon a trigonal planar arrangement. But what if carbon forms a triple bond? The geometry changes once again. And to see this in action, let's look at ethane. In this case, carbon combines one s orbital with a single p orbital. The result is two new identical orbitals called SP hybrid orbitals, plus two original unhybridized p orbitals left over. Each carbon is involved in a triple bond, and now the geometry is completely different. With only two hybrid orbitals to arrange, the most stable configuration is to point them in exactly opposite directions. A perfectly straight line, 180 degrees apart. The two leftover p orbitals sit at right angles to that line, and at right angles to each other. Each carbon uses its two sp orbitals to bond outward, one to hydrogen, one to the other carbon, creating that signature linear geometry. So we've got three hybridization types, three shapes, three bond angles. But there's a pattern connecting all of them that most students miss. That fascinating consequence of hybridization is S character. In sp3 hybridization, one out of the four hybrid orbitals originates from an s orbital. So each sp3 hybrid orbital has 25% s character. In sp2 hybridization, one out of three orbitals comes from the s orbital, giving each hybrid orbital about 33% s character. And in sp hybridization, one out of two comes from the s orbital, giving each hybrid orbital 50% s character. As you move from sp3 to sp2 and then sp, the percentage of s character keeps increasing. But why does that matter? Remember, an s orbital has its electron density concentrated closer to the nucleus than a p orbital. So as a hybrid orbital gains more s character, its electron density is held closer to the nucleus, and bonds get progressively shorter and stronger. The carbon-carbon bond in ethane is the longest and weakest of the three. The bond in ethylene is shorter and stronger, and the bond in acetylene is the shortest and strongest carbon-carbon bond of them all. Same two carbon atoms. But different hybridization results in different s character, bond length, and bond strength. This is where hybridization becomes incredibly useful. Once you identify the hybridization of a carbon atom, you can predict its approximate geometry. You can understand the direction of its bonds. You can anticipate whether the carbon is tetrahedral, planar, or linear. And it gives us a powerful bridge between something microscopic, atomic orbitals, and something we can actually visualize, the three-dimensional shape of a molecule. But there's still one important piece missing. We've talked about hybrid orbitals, but what about the unhybridized p orbitals left behind in sp2 and sp hybridization? What exactly do they do, and how can a carbon atom use them to create the additional bonding interactions found in double and triple bonds? That's where sigma and pi bonds enter the story in next episode. If hybridization finally clicked for you today, hit subscribe. This series is building towards some of the most satisfying aha moments in all of organic chemistry. See you in episode 5.